So basically we have about 25 minutes. It may be a little bit less now because of our technical difficulties. So Audrey will present for a portion of the time, and then I welcome you all to join me for a bit of a conversation at the end. So feel free to leave on your video, and I'll be trying to monitor the chat so you can put any questions in there, and we'll try to queue up some questions for the end. And now just to introduce myself a little bit. So I'm Sandra, and I was a 2015 Schulich leader at Queen's. So in my undergrad, I studied engineering chemistry, which is basically a mix between chemical engineering and chemistry. So I decided to stay at Queen's to do my, so I started my master's in 2019 and just promoted to my PhD in chemical engineering in May of this past year. So I'm doing some work in this green chemistry field, trying to replace solvent-based technologies with water-based technologies. So to do this, we use something called emulsion polymerization, which you have to mix oil and water phases together somehow. So we use these industrial soaps, usually called surfactants, but these can be toxic and leach from products. So our group is developing some greener alternatives in the form of other types of polymers. So I'd just like to take a couple minutes to introduce Audrey now. So Dr. Audrey Moores is a professor of chemistry and was the Tier 2 Canada Research Chair in Green Chemistry from 2007 to 2017 at McGill University, where she started her independent career in 2007. She was elected in 2020 as a member of the College of the New Scholars, Artists, and Scientists of the Royal Society of Canada. So she completed her PhD at École Polytechnique France in 2005, where she was also awarded the Best Thesis Award. Following this, she completed her postdoctoral fellowship at Yale University, funded by a Lavoisier Fellowship from the European Union. Audrey is a leading expert in the field of catalysis using metal oxide, and biomass-based nanomaterials, with a special emphasis on sustainable processes and use of earth-abundant starting materials. Her scientific work has been published in over 80 high-profile, peer-reviewed. Can I just have everyone put their mic, put their audio on? The MIT Media Lab in the States, a Master of Arts from the Royal. Okay, I think we got it. So her work has been published in over 80 high-profile peer-reviewed publications, and she has authored 7 book chapters, 1 book, and 3 patents. Her research was recently highlighted in Nature in 2016, and she was selected as an emerging leader in 2017 by the Royal Society of Chemistry journal Green Chemistry. And without further ado, I'd like to welcome Audrey to the floor, and she'll start off with a presentation for us.
Hey, thank you so much, everybody, to be here today. And it's really a pleasure and an honor for me to be talking to you, Schulich leaders. This is just fabulous. As Sandra mentioned, and thank you so much, Sandra, for this wonderful introduction. I've been a part of a few things, and I'd like at the end, so I'll talk a little bit about science and stuff, but I'd like at the end to sort of circle back to the notion of leadership and how we can, even in science, even in research, even in green chemistry, be leaders in our own way. And I'd love to really have your thoughts on that as well. I'll share some of my ideas, but hopefully you can also bring a lot to the table. So what I want to do today is I prepared a few slides, but not too much, hopefully. And what I try to do is talk a bit and really try to get you to react and ask questions and talk to me, because I really want this to be as much as a dialogue as is feasible. So I'll try to throw at you a few concepts, a few ideas of things that we've been doing, and then you can intervene, use the chat box. Sandra will interrupt me as well, I'm sure, and we could get the ball rolling. So thanks so much. What I wanted to ask you is, what do you think is the common points between all of these things that are on my slide here? These are things that are around us. You have paints, you have fabrics, you have drugs, and I have this beautiful tree here. What do you think is common in all of these things that you have on the slide. Is there an idea from the audience?
Feel free to jump in the chat to put your answers here.
Yeah, actually, this is almost true. Yeah, polymers. I mean, I was after something even a bit more general than that, but you're right that at least 3 of them have polymers in them. Chemistry. Thank you so much, Tony and Liam. So what I was trying to get at here is that if you turn around and you look at anything that's around you, including your own computer, you have chemistry everywhere. And this is what I like. As you know, my passion is really in chemistry. I delved into it when I was pretty young, and I just never stopped doing it. But what I think is fascinating about it is that it really is everywhere. It helps build everything that we have made and everything that nature has made as well. And by being smart about it, shrewd about it, by knowing what chemistry is, we have enormous powers to actually change the world and do new things. So that's really where I wanted to start. So that's really where my passion lies, and I'm trying to use in my life chemistry to try to see if I can do things a bit better. So if you look at chemistry, I'm sure some of you, I'm sure you've taken a chemistry class at some point. Some of you may have hated it. Some of you maybe liked it, hopefully. But I think one thing that I want to take away from any chemistry is that usually when you do chemistry, you draw an arrow between something that we call a starting material or a feedstock, and then it goes into a product that you could sell, for instance, or that you could use, or that you could, where you can transform the world with these products, like if you're making a drug that can cure a disease. And I have put here some stuff on the top and bottom of this arrow, which are things that we need in order for this transformation to happen, from the feedstock to the product. So that's a very, very general way we can see chemistry. Chemistry is just helping transform stuff into a resource to something useful, and we use a ton of things around it. So what we do in green chemistry is we're trying to take this thing and we then try to put it inside a bigger, we're trying to take it and we try to put it inside a bigger context. We're trying to put all of that inside an ecosystem. We like to talk about systems thinking right now in green chemistry. So it's really this idea that now, where is my feedstock coming from? Where is my product going to go? Where is it going to go when it is in the product it's supposed to be in, but also where is it going to go after life? And then all of this process that I mentioned, it uses these weird things like catalysts and medium and energy. I'm not going to go into the details, but essentially, where are these things coming from? Where are they going after it? And can we reduce the impact that they have in general? So this is really how we view green chemistry, and this is some of the examples of where this thought process has been taking us. So some people, for instance, thought, okay, we're using detergents and they end up in the environment, some of which can be harmful to the environment. So people have tried to design bio-based stuff, especially here, things based on essential oils that are extracted from nature. So this is an example of a formulation of a detergent in which the antibacterial part that used to be a harmful chemical now is coming from extracts of thyme. And what this means is that it's not permanent in nature, and then it also is not harmful in nature. Another thing that you might have heard of is people are trying to replace fossil resources, especially in the sector of energy. There's a huge field in green chemistry that is looking into how we could use other sources to make energy and make fuels without having the impact that fossil resources have. Another example is at the bottom here. So you know that there's very strict regulations around selling products so that they will not catch flames. That's very important to protect our houses in case, unfortunately, a fire gets into the house. So a lot of products, furnitures, clothing, and so on and so forth, have what we call flame retardants, which is essentially mean that they're not going to catch flame so easily, and it's leaving people time to leave the building. But a problem occurred when these things actually end up in our environment, because some of them are toxic, some of them are permanent as well, and bioaccumulate. So they can go inside our bodies, they can go also in nature and do harmful things. So green chemists, they came to the rescue, and there's been a number of molecules that have been developed that are innocuous, yet still help with this flame retardancy. And finally, and I'll talk briefly about this at some points, is this notion of plastic. So I'm sure you're all aware that we are using single-use plastics way too much, and they end up in the environment and they do an awful lot of harm. And also we would like to recycle them, but we don't know how to do this as efficiently as we should and as we would like. So there's lots of green chemistry that is being developed there around either making biodegradable plastics that truly degrade when they go in nature, or plastics that we can recycle even more easily so that we can develop this circular economy that a lot of people are talking about. So these are just some really vignette examples, snapshot examples. There's a lot more to delve into. But what I wanted to say is that this idea of doing chemistry better is something that is really powerful, because a lot of the problems you have out there, they require a technical solution that is chemistry. So I just would like to end this little segment by this thing. So I was wondering what you guys are thinking of when you see this. When you see this image, what comes to mind? What's the first thing that comes to your mind? Food coloring. Yeah, that's interesting. That's true. Yeah, chemistry again. Experiments. Yeah, green chemistry. Yes, exactly. So I think so. You have experiments, food coloring. So you know, I think your answer is around science and chemistry. Am I right? So this is the first thing that comes to mind when you see this. So I don't know what you see, Sandra, when you look at this this picture. What do you think of? Science education. Yeah, it's a good one.
Yeah, I see some science education. I see trying to make chemistry more appealing to the public, maybe.
Yeah, that's true. That's true. But you mentioned the term in your own introduction that I think is very relevant as well for this image, right?
Some green chemistry.
Yeah, some green chemistry, but this also, everything that you see here is a liquid, right?
Yes.
So in chemistry, we call them solvents. So what's really interesting is that when I see this image, I see solvents, I see liquids. But you guys, you see chemistry, science education, experiments. What I'm trying to get at here is that our brain are so wired to think science and chemistry is about manipulating liquids that sometimes we forget that we can do chemistry with other things but liquids. And I don't know, maybe I'll open it up to a few questions now, but when I come back to more, I will show you how we're doing chemistry without liquids and how this can change and actually transform, I think, the way we think about some of the big problems we have out there. So do you guys want to ask some questions at this point about green chemistry, about challenges to the environment, about sustainability?
I think maybe if we keep going for now, since we lost a little bit of time with that.
Sure, no problem. Let's do that. Let's do that. Absolutely. So, okay. So what I'm trying to get at now is that I think it's really something quite remarkable that chemistry was developed for a huge amount of time, really solely on doing things in liquids. So that's the image there. And the reason why it happened is because when you take something and you mix it inside a liquid, you dissolve it, right? Then often it becomes more reactive. So it's a bit easier to take it and then partner it with another chemicals and then make the reaction happen, and then you make your product. But in doing so, people forgot completely that sometimes things also happen in absence of a solvent. And then it's very nice because solvents, they account for the largest quantity of waste that the whole chemical industry is going to provide. So if you look at, drug industry, petrol industry, detergent industry, everything we call commodities in chemistry, all of these things, the largest waste that's coming out of this is these liquids that we use as a medium for the reaction to happen. This is a huge problem because these waste are, we have to dispose of them. They can cause some pollutions. They can cause a lot of problems. They can go in the environment and cause VOCs and all sorts of stuff like that. So my group and a bunch of other groups were looking at doing chemistry a different way, absent of any solvent, or, at least reducing largely the quantity of solvents. We're not completely out of it, but mostly out of it. So the idea is very simple. I mean, this is a mortar and pestle. I'm sure all of you have seen one before. Maybe you're using one in your kitchen, I don't know. And what you do there is you mix stuff in the solid phase, and this is and you can make reactions happen this way. In fact, some of the most ancient reactions that were discovered were made via mortar and pestle. In the modern world, you have different ways of doing that now. You could use different machines that allow to mix powders together with different bowls. You could see these things that are vibrating, these things that are rotating. Even extrusion is a form of solid state reaction where two products can be fed in here and massaged together, mixed together. And we find that at the end, we can make products this way very, very effectively. Another thing that we've been doing in my group is actually even more drastic, is to say, okay, let's mix things together and let them react together by what we call aging. So just letting things sit together, and then over time, chemical reactions happen. And we find that when we do this, we have fabulous opportunities to, one, get rid of solvents, but even sometimes get better chemistry. We found that we have better yields, better results. So I'll give you an example of that, of how we used it. So we have a big problem out there. We're eating a lot of food, and in particular, one of them is seafood. And seafood waste is a big problem around the world. It's considered that there's between 6 million and 8 million tons of waste just from crab, shrimp, and lobster industry every year. And this waste, in particular, the carapace of these animals, is very rich in really nice chemicals that we can use for high-end applications. And it's difficult to extract these chemicals because we don't have very good ways of doing it. So there's been a lot of efforts for a bunch of people to highlight these resources as really great way that we could get some nice chemicals. One thing that it would do too is it would allow you to use a waste that is causing a lot of pollution. So if you take this and you dump it back into the ocean, it creates a lot of really bad pollution locally. And this is a big environmental problem as well. So that's something that we need addressing. So if I look at the carapace of a lobster here, what is inside the lobster is actually three components. You have a blue thing here that is a polymer called chitin. You have another polymer called, made of proteins, that is here in orange. And then you have some minerals, like little stones in there. And what happens when you do this is what you want to extract the chitin, because chitin is a very interesting polymer. So there is a method to do it traditionally, but it's very, very intensive in chemistry. It's very harsh chemicals. And the problem with that is that this chemistry that currently is used around the world to extract a product called chitosan. This product here is used for making sutures, water filters, and for making antibacterial materials. It's a molecule that has a huge market potential. It's growing every year. But the problem is that this one method that everybody uses around the world is uses corrosive liquids and very high temperatures. And more importantly, they generate a huge amount of wastewater that is very toxic. So in Canada, we make a lot of lobster, right? I'm sure you've had the chance to eat one day. But the problem is that nowhere in Canada do we make chitosan, this high value molecule. Why? Because of this effluent here. These effluents are just complete killer for the industry. They used to be plants, they all shut down. So what we did in my group is we decided to transform this, and we created a path here to a new form of chitosan that is actually higher quality than the one we make here. But we made it completely in a solid phase by using a mechanochemical aging method. So I'm not going to go into the detail, but essentially we use 8 times less chemicals. We use more than 3 times less energy to make it, and it's much safer to the operators around. And we use about an order of magnitude less water too, which again taps into this idea that we're not going to have so much waste at the end. And right now we're working with a bunch of people. Sorry, I want to share this, you this. Right now we're working with a bunch of people to try to establish a plant doing this in the north coast of Quebec over here, and also in Gaspésie over here. And this is really interesting because we're generating a huge amount of waste in Quebec, but also in the Maritimes. And we're also talking to people there. So you can see here the huge potential for producing these kinds of things in Canada. Another thing I wanted to show you is these two people that are working in Parks Canada. What they're doing here, especially Chris there, is they're collecting these green crabs from this little park here that you can see on the shore of Nova Scotia there. There are some Nova Scotian on the call, hi to you. These guys are really nasty invasive crabs that are destroying ecosystems along the shore there. And they've developed this system where they can collect them, trap them, and by doing so, they can actually recover the ecosystems inside these beautiful parks. So we've partnered with them, and we're collecting these crabs that you can see here. So they collect that, and then they send it to us, and we demonstrated that we could take these crabs and turn them into, again, high quality chitosan. So the idea would be to work with commercial fishermen, but also try to also help an ecological problem there by extracting these guys and turning them into useful compounds. So that's another example of what we've been doing. So ultimately, what we're doing here is we're making some green chitosan locally produced in Canada, and some of the outcomes we could have where we're working with different companies to see if we can make fertilizers, water treatment systems, biomedical applications, and or bioplastics. So I just wanted to see if you guys had some questions, and then I can close on a few thoughts on leadership afterwards if we have a few minutes more. I'm not sure how time is anymore.
Yeah, I've been told we have till 3:25, so maybe we can just try to have a little bit of a conversation around the green chemistry part of your talk, if that's okay.
Sure. Yeah, sure.
Yeah, and I can start off with a question. So when we're talking about green chemistry or green technology in general, how do we know whether something is truly green or if we may be making the issue worse?
Yeah, no, that's a great point. So in green chemistry, some of the thought processes people have had is that often chemists want to do something really cool, and then later, 20 years later, 50 years later, we realize that this really cool thing eventually accumulates in the environment and is really bad. So what we're trying to do as a community is to develop tools to measure how green something is, and we call them life cycle assessments. So there's a number of different things that are going into there, but the idea would be for any process to measure from the resource all the way to the end of use and disposal. What is the energy usage? What is the how much this accounted for global warming gases? How toxic this is? How toxic it is, and so on and so forth. So you have a bunch of criteria, and what you do with this data, and you try to make wiser decisions. So nothing's perfect. There's no silver bullet. Nothing is a magic replacement. But what you can do is to learn as much as possible and try to make a better replacement from what you have right now.
Yeah, when I think about life cycle assessments, I think the first thing that pops into my mind is plastic versus paper versus reusable bags. I don't know if you want to comment on that a little bit.
Yeah, so that's the famous example from Phil Jessup, he's a good friend of both of us. Yeah, so I mean, everybody's like, oh, let's use the paper bag. But when you realize how paper bags are made and impact on the environment